Sazzad, take over maybe.
Yeah. So good afternoon, everybody. So I'm very happy to introduce Professor Sandeep Varma from Tata Institute. So today he will be speaking some result of Borel-Harish-Chandra in this trimester. So, and this will be his second talk. So over to you, Sandeep.
Thank you, Professor Biswas. So let us continue from yesterday, though we'll start on a different note from where we stopped yesterday. So last time we discussed SL M of R modulo SLM of Z. Now we'll start discussing SO of M comma Q. Okay. So in other words, let us consider the space Q to the M, the M-dimensional Q vector space, and consider a non-degenerate quadratic form little q. Okay. In other words, little q of x is like a1 x1 square plus up to an xn square plus some linear combinations of the xi xj. Okay, we can also write it as bq of x comma x, where b is a bilinear form, non-degenerate bilinear, symmetric bilinear form. Okay, so the group that we are interested in is SO of Q, the orthogonal group of the quadratic form Q. Okay, so remember Q is the quadratic form and it is not the dimension. The dimension is M. Okay, so what are the R points of G? G of R is SO of Q comma R, which is the set of all elements G in GLM of R, which preserve the quadratic form. Preserve the quadratic form means for every vector x in Rm, you are imposing the condition that Q of Gx equals Q of x. Okay, so those G constitute the special orthogonal group of the quadratic form. If you take the quadratic form to be x1 squared plus x2 squared up to xm square, then the group G you get is the usual compact orthogonal group. But otherwise, these orthogonal groups can be more general than that. Okay, so you have SO of Q to the M comma Q. Okay, in general, if you have a vector space V and a quadratic form Q on it, we would denote by SO of V comma Q, the associated orthogonal, special orthogonal group. Okay. Sorry, there is a typo in the line. So the definition Q of Gx equals Q of x only defines the orthogonal group. So for the special orthogonal group, I need to additionally impose that the determinant is 1. Okay, if it preserves the quadratic form, the determinant can be plus or minus 1, but I actually need it to be 1. Okay, sorry for that. And the same thing with the next line, G of Z. Okay, so G of Z is what I'm defining it to be G of R intersection GLM of Z. Okay, so namely G element of GLM of Z. And again, I have missed the condition. Q of Gx should be equal to Q of x for all x and determinant of G is equal to 1. Okay, so those conditions are there. Okay, so now you see the quadratic form is defined by a bunch of equations over Q. Okay, so you can talk about G of A when A is any ring containing Q because you are solving the equations over the ring A which contains Q. Okay, so the equations make sense over A also, but G of Z does not a priori make sense. So we are defining it slightly artificially. We are looking at G of R, which is contained in GLM of R, and then intersecting it with GLM of Z. It's a slightly artificial definition, but then we are defining it that way. Okay, so you have G of R, which is the special orthogonal group, R points of the special orthogonal group, and then you have G of Z, which is obtained by intersecting with GLM of Z. Okay, so the question is, what are the various Q? Given a Q, how can you say whether or not G of R modulo G of Z is compact? Okay, yesterday we considered the question of compactness of SLM of R modulo SLM of Z. This time the same thing with SO. Okay, so what is the reason why we took the quadratic form Q, little q, to be over capital Q than over R? Okay, so the point is, I associated these groups G of R and G of Z to a quadratic form Q over R, Q over Q, right? But if I replace it by an isomorphic quadratic form, is G of R going to be same? And the answer is yes, because you know the quadratic forms are isomorphic over Q and therefore they are isomorphic over R. Okay. By the way, what does it mean to say that two quadratic forms are isomorphic? It means that each quadratic form can be obtained from the other using a linear change of variables. Okay, that's the meaning of isomorphic quadratic forms. So if two quadratic forms are isomorphic, Q1 and Q2, then G1 of R and G2 of R are also isomorphic, but G1 of Z and G2 of Z are not isomorphic. Okay. So the resulting isomorphism G1 of R to G2 of R, it does not take G1 of Z to G2 of Z, but it takes G1 of Z, it takes a finite index subgroup of G1 of Z to a finite index subgroup of G2 of Z. Okay. So since this works well with respect to finite index subgroups, G1 of R modulo G1 of Z is compact if and only if G2 of R modulo G2 of Z is compact. Okay. So this is true if little q is taken over q. Okay. If you took q to be a quadratic form over R and replace it to be with an R isomorphic quadratic form, this compactness would not have been preserved. Okay. You can easily play with some small dimensional examples and check. So that's why we are taking these over q. Okay. So before getting on to the question of when is SO of QR mod SO of QZ compact, when is G of R mod G of Z compact, let us look at an easier question. When is the special orthogonal group itself compact? Okay, so all of you know the answer. When is an orthogonal group of a quadratic form compact? Let's just review it. Okay, so over R, what are the isomorphism classes of quadratic forms? In Artin's algebra book, we study what is known as Sylvester's law of inertia. Okay, what does that law say? It says that non-degenerate quadratic forms Q on Rm up to isomorphism are in bijection with pairs A, B of non-negative integers that add up to M. Okay, A, B is called the signature of the quadratic form. Okay, so if A, B is the signature, then your quadratic form is isomorphic to x1 squared plus x2 squared up to plus xa squared minus xa plus 1 squared minus xa plus 2 square up to minus xa plus b square. So you have a pluses and b minus signs. Okay, so that is the definition of the quadratic special orthogonal group SO of A, B. Okay, so our usual compact orthogonal group SO of M is actually SO of M, 0. Okay, it is also isomorphic to SO of 0, M, because from a negative definite form, you can go to a positive definite form by multiplying by -1. So before asking when is SO of R mod SO of QR mod SO of QZ compact, let us ask the easier local question of when is SO of QR compact. Okay. So here is an easy fact that one can prove. SO of A, B of R is compact if and only if AB is either M, 0 or 0, M. Okay, so if A, B is M, 0, it's our usual orthogonal group SO of M. And if it is 0, M, then also it is usual orthogonal group 0, SO of M, because you can just multiply the quadratic form with -1. That does not change the orthogonal group. Okay, so this is equivalent to saying that Q is either positive definite or negative definite. Okay, so here is some hint on how you might prove it. Okay, so if A, B is not, if one of A and B is not 0, then what do? Then the quadratic form Rm, Q contains as a subquadratic form a copy of R2, x square minus y square. Right? You can take x square, xa square minus xa plus 1 squared. Right? That xa square minus xa plus 1 squared is a quadratic form of the isomorphic to R2, x square minus y square. And if you compute the special orthogonal group of that, it is GL1. Okay. So if neither A nor B is 0, then your orthogonal group is going to contain as a closed subgroup a copy of GL1. And you know that compact orthogonal groups cannot contain a copy of GL1. They can only contain copies of S1, right? So an equivalent way to say this is the following. Okay. To say that a quadratic form is positive definite or negative definite is the same as saying that for every non-zero vector in Rm, the quadratic form is non-zero on it. Okay. So for all 0 not equal to W element of Rm, Q of W not equal to 0 is the same as saying that Q of W is either always positive or always negative for non-zero vectors. Okay. So we might as well say SO of Q, R is compact if and only if Q is anisotropic over R. Anisotropic means Q is never 0 on non-zero vectors. Okay. So unlike positive definite or non-negative definite, the notion of anisotropic depends only on whether or not the quadratic form is This can be defined. The notion of anisotropic works over any field, whereas positive or negative definite works only over the field of real numbers. Any questions?
So I have a question.
Yeah.
So this result is for Archimedean local field, this, but however, non-Archimedean local field, is there any result?
Exactly. So I'll come to this. So over non-Archimedean local fields also, an orthogonal group is compact if and only if the associated quadratic, orthogonal group of a quadratic form is compact if and only if the quadratic form is anisotropic. Okay.
Same. The
Sorry?
result will hold.
The same result will hold, and that is why we need the notion of anisotropic. Positive definite and negative definite do not make sense over non-Archimedean fields, but anisotropic makes sense.
Okay. Okay.
Yeah.
Okay.
So please remember this definition of anisotropic. We are going to need it. Any question? Any more questions? Okay, so let me go ahead. So this is what I was saying. So if W is a finite dimensional vector space and Q is a quadratic form on it. Okay, so in other words, it's of the form B of V, comma V. Q of V is B of V, comma V, where B is a symmetric non-degenerate quadratic form. Sorry, I made a typo here. Q should not be an arbitrary quadratic form. It should be a non-degenerate quadratic form. Okay, so that's a second typo that I have made. Then the following are equivalent. W, comma Q is isotropic. That is, it's the opposite of anisotropic. Okay, that is, there exists a non-zero vector W on which Q of W is 0. That's equivalent to saying that SO of W, comma Q contains a copy of GL1. Okay, I'm calling the group GL1 GM. So please remember the notation GM. It's going to be used in the subsequent slides. Whenever I read GM, I just mean GL1. Okay. So in other words, an algebraic group, the corresponding algebraic group contains a copy of GL1. Such algebraic groups are called isotropic. So isotropic as a linear algebraic group is related to isotropic for a quadratic form. Okay. So in other words, our previous result can be summarized as saying that for a special orthogonal group G over R, the Lie group G of R is compact if and only if the linear algebraic group G as an algebraic group is anisotropic over R. That is, it does not contain a copy of GL1 or GM. Okay. And this generalizes to reductive groups over R. Namely, if G over R is any reductive group, G of R as a Lie group is compact if and only the algebraic group G does not contain a copy of GM. That is, it is anisotropic. Any questions? So the next comment is that the same statement is actually true with R replaced by any local field K. In fact, for local fields, of course, although this result is classical, there is a very recent new proof by Gopal Prasad as part of his new approach to Broughart-Its theory. In his paper, Broughart-Its theory, a new approach. And it's also there in the book of Gopal Prasad and Tasho Kaleta. Okay. So now let us move on to the global question. When is G of R modulo G of Z compact? Okay. So that's a harder question than G of R being compact, because G of R being compact was in some sense Lie groups or group theory, whereas G of R mod G of Z being compact is number theory. Okay. And number theory is always harder. In a sense. So remember the setting. Little q is a non-degenerate quadratic form on Qm, and G is the special orthogonal group of that quadratic form. And I define G of Z to be G of R intersection GLM of Z. Okay. So if G of R happens to be compact, that is Q is anisotropic over R, please note the blue, because over R is very important for this. Then because G of R is compact, then G of R modulo G of Z is also compact. However, as we are going to see, it can happen that Q is not anisotropic over R, and yet G of R mod G of Z will be compact, although G of R is not compact. Okay. So here is a statement. Very interestingly, G of R mod G of Z being compact is also related to Q being anisotropic, but this time the difference is that Q is required to be anisotropic over the rational numbers and not the real numbers. Namely, for every non-zero vector W in Qm, Q of W should be non-zero. Okay, is the statement of the theorem very clear?
Yes. Yeah.
Thank you. Okay, so let us look at the meaning of the statement for two examples. Okay, I'm going to discuss two examples of, firstly the quadratic form q of xy equals x square plus dy square, and secondly the quadratic form x square minus dy square. Okay. So in the second example, we are going to see a little bit of number theory. So that will give you a taste of how this theorem is related to number theory. Okay. In the first case, when the quadratic form is x square plus dy square with d positive, then the quadratic form is anisotropic over both q and r, right? If not, if one of x or y is non-zero, x square plus dy square is going to be non-zero. Okay. And in this case, everything is easy. Both g of r and g of r mod g of r is compact, and therefore g of r mod g of z is compact. However, the second example is more difficult, because if q of xy is x square minus dy square, then q is isotropic over r. Okay, because you can consider the non-zero vector root d comma 0. Okay, root d comma 0, on that q is 0. Therefore, over r, q is certainly isotropic. However, root d comma 0 is not a rational point in general. So it follows that q is isotropic if and only if d is a square of an integer. Okay. If d is not a square, then it is easy to see that q of xy is anisotropic. So let us see why g of r mod g of z is still compact as the theorem predicts. Okay. So please understand this example. It's going to be important. I mean, you don't need it to follow the subsequent slides, but it's a good example to know. Okay, so in this case, you can make this computation. I should have rechecked the computation, but anyway, let us accept this for now. G of r consists of matrix of the form A, db, ba, which satisfy the property that a square minus db square is 1. Okay, so this is like a matrix representation of the number a plus square root of d times b, and therefore g of r is actually going to be isomorphic to r star. Okay. You are only looking at those a and b such that a square minus db square is 1. Okay. So these are like, a square minus db square. Note that it looks like the norm from q of root d to q. Okay. So suppose d is a square. Okay. In the case where d is a square, then a square minus db square equals 1 has no integer solutions other than some simple solutions like plus or minus 1, right? Because if d is a square, then db square is also a square, and two perfect squares cannot differ by plus or minus 1 unless they are very small. And therefore, g of r mod g of z is just r star modulo plus or minus 1, and that is certainly non-compact. Okay. So the interesting case is when q is anisotropic over r. Okay, in which case, let us see what happens. If q is anisotropic, then d is not a square. So q of root d is actually a quadratic number field, and g of z is the set of all a plus b root d in z of root d, such that the norm of that a plus b root d is equal to 1. Okay. So approximately, okay, so I'm not being very rigorous. Approximately, g of z is the set of units in the ring of integers of the quadratic field q of root d. Okay, so let me repeat that because it is important. G of z is approximately the group of units of the ring of integers. Okay, z of root d is very close to the ring of integers of q of root d, and g of z looks like the group of units in that. So Dirichlet unit theorem says that g of z contains a copy of z. Okay, so in q of root d, the ring of integers has a non-trivial unit group generated by a fundamental unit. These are solutions of the Pell's equation. So it says that you are quotienting out r star by g of z, which contains a copy of z. If you quotient r star by an infinite cyclic group, obviously the quotient is going to be compact because r star almost looks like r up to plus or minus 1. Okay. So in this case, g of r mod g of z is compact if q is anisotropic, as the theorem predicts, but this involves Dirichlet's unit theorem. Okay, any questions? Okay, let me go ahead. Okay, so we'll slowly discuss a proof of this theorem. And this is going to involve Mahler's compactness criterion. Okay, from last time, which I'll recall. Okay, we'll not revisit the proof, of course, but we'll revisit the statement now. So remember that little q was a quadratic form on capital Q to the m, rationals to the m, and therefore the special orthogonal group is actually contained in SLM of Q. Okay, proving the theorem will have two steps. First of all, SO of Q comma R modulo SO of Q comma Z, that is G of R mod G of Z, sits inside SLM of R modulo SLM of Z. Okay. As the first step, we will show that this injection is a proper map in the sense of topology, point set topology. Proper map is a map for which the inverse image of a compact set is compact. A proper map also has the advantage that as long as the target is locally compact, Hausdorff, it takes closed sets to closed sets. Okay, the image of a proper map is actually closed. Okay, so it's a nice kind of map. Why are we showing that? That step has the following advantage. To test that SO of QR mod SO of QZ is compact, it's enough to show that its image in SLM of R mod SLM of Z is compact. Okay, so in other words, we can look at the image in SLM of R mod SLM of Z and apply Mahler's criterion, which we had seen last time. Okay, so we want to show that the image is compact if and only if the quadratic form Q is anisotropic. Okay, so I'm going to skip the proof of the first step, though we will revisit you during the adelic treatment if we have time. As usual, I have started going out of time, but anyway, so let us discuss, let me recall the Mahler compactness. Okay, so from last time I stated this theorem. Our interest was in the space SLM of R modulo SLM of Z. Okay, and we saw that this space can be identified with the space of unimodular lattices L contained in Rm. Okay, what was unimodular? A lattice in Rm is said to be unimodular if its co-volume is compact. That is Rm modulo that lattice, has volume 1. That is Rm modulo L with the induced measure has volume 1. Okay. And how did we identify this with the space of unimodular lattices? Given G in SLM, you send it to G inverse times the standard lattice Zm. Okay, so the stabilizer, so G inverse Zm is equal to Zm if and only if G belongs to SLM of Z. So the quotient SLM of R mod SLM of Z is identified with the space of unimodular lattices. And the statement was that a subset of SLM of R mod SLM of Z is relatively compact if and only if, you are viewing this as a space of lattices, it avoids a ball around 0. What does that mean? There exists some delta greater than 0 such that if you take any lattice in your collection, every non-zero vector of any of these lattices has to have absolute value. Any non-zero vector should have length greater than delta. Okay, so a collection of unimodular lattices is relatively compact if and only if there is a delta which bounds from below the lengths of the non-zero vectors in all of these lattices. Okay, so relatively compact equals avoids a ball around 0. Any questions? So we are going to use this result and prove the theorem. Okay, so here all that I have done is I have copied and pasted the stuff from last time, and we now want to reformulate Mahler compactness. I stopped around this point when I was slightly confused. Okay, so we want to see when a set of lattices inside Rm satisfies this condition that it is contained in some S of delta. Okay, so note that for a set L of lattices in Rm, the following are equivalent. L is contained in some S of delta if and only if L avoids a ball around 0. So a complicated way of saying that, which somehow happens to be useful for us, is that take any sequence of lattices in the set L of lattices. Okay, so Ln is any sequence of lattices, and take any Wn in Ln. Okay, the limit of Wn is 0 if and only if Wn is 0 for all large enough n. Okay, so why is this equivalent to L being contained in S of delta? L being contained in S of delta is the same as avoids a set of delta ball around 0, right? If you avoid a delta ball around 0, a sequence in that is not going to be able to converge to 0. Okay. So if you have a set of elements which are all contained in a delta ball around 0 or are 0, those can only tend to 0 if it is eventually, like, if those elements are eventually 0. Okay. So one way of saying is that a sequence of lattices is contained in S of delta is that a set of lattices is contained in S of delta is that take any sequence ln from this set, take any set of sequence of vectors wn with wn belonging to ln. The limit of wn cannot be 0 unless wn is eventually 0. Any question? So let us reformulate Mahler compactness using this. Okay, so we will only need the reformulated version of Mahler compactness. Okay, so remember we are identifying unimodular lattices with SLM of R mod SLM of Z. So the statement is that you are given a subset in SLM of R. It has a relatively compact image in SLM of R mod SLM of Z if and only if you take any sequence Wn in Zm and take any Gn in M such that limit of Gn inverse Wn is equal to 0, then the Wn have to be eventually 0. Okay. So why is this equivalent to Mahler compactness? The way you translate from this statement of the theorem to the equivalent condition that I have written in terms of a set of lattices is that the way you identify SLM of R mod SLM of Z with lattices is using the formula G goes to G inverse Zm. Okay. So what is Wn in the equivalent condition that I stated earlier in terms of the set L of lattices is actually Gn inverse Wn in terms of the last in the formulation on this page. Okay. So you need to remember only the formulation that I have written at the below at the bottom in this page. Namely, a subset of SLM of R has relatively compact image in SLM of R mod SLM of Z if and only if you take any sequence of vectors in Zm, you take any sequence Gn inside your set M. If the limit of Gn inverse Wn is 0, then the Wn are eventually 0. Any questions?
So we are doing this to prove the GR mod GZ is compact if and only if Q and S.
Very good. Yeah. So let me state that once again. We wanted to study when GR mod GZ is compact. Okay. Our first step was to show that GR mod GZ is compact if and only if its image in SLMR mod SLMZ is compact. Okay. That needs a proof, but I have skipped it. So now what we are trying to prove is that the image of G of R mod G of Z in SLMR mod SLMZ is compact if and only if Q is anisotropic. Okay. So why did we have to reduce to this? Because we only have a compactness criterion for SLMR mod SLMZ. You see, we had to work a bit hard last time, right? We had to work with arbitrary lattices and we had to choose different bases. If we had to do that with respect to arbitrary linear algebraic groups instead of SLM, it's going to be hell. Because if you take G of Z, these will be lattices with very horrible properties with respect to very badly positioned quadratic forms. So we needed to transfer the question to SLMR mod SLMZ. That was the first step. And we are now trying to study the image in SLMR mod SLMZ. Does that answer my question? Answer your question?
Yeah.
Any other question? So, so this last question, last statement is what we need. Okay, so let me give the idea of the proof that G of R mod G of Z is compact if and only if little q is anisotropic over q. Okay, so q was a rational quadratic form, and without loss of generality, I am assuming that q takes integer values on integers, integer points. Okay, why can you assume this? Because the orthogonal group is unchanged if you multiply q by a non-zero number. So I can always multiply q by a non-zero integer and assume that it has integer coefficients. Okay, so this is going to be a convenient assumption. And then we'll do it in two steps. We'll first assume that q is anisotropic over q and show that GR mod G of Z is compact. Secondly, we'll assume that q is isotropic over q and show that G of R mod G of Z is not compact. Okay, so let's do the first one. Suppose a sequence Gn inverse Wn tends to 0, where each Gn belongs to G of R. Okay, G of R is contained in SLM of R and Wn is an integer vector. We need to show that Wn are eventually 0, right? This was the condition I stated at the end of the previous page. Okay, even if you don't remember the condition, you can just take this on faith. So we know that Gn inverse Wn goes to 0. We want to show that Wn is eventually 0. We are given that Q is anisotropic. Okay, so what do you do? The obvious thing to do is to apply Q. Okay, so just apply Q. Q of Gn inverse Wn is the same as Q of Wn. Okay, and because Q takes Zm to Z, Q of Wn is an integer. So we know that Q of Gn inverse Wn goes to 0, but that is Q of Wn. So Q of Wn is a sequence of integers that go to 0. Okay, so if a sequence of integers goes to 0, it has to be eventually 0. However, now we use the fact that Q is anisotropic. So if Q of Wn is 0, then Wn itself has to be 0. So it follows that Wn is 0 for large enough n. Okay, so that shows that G of R mod G of Z is compact. Okay, so look at the power of Mahler's criterion. Dirichlet's unit theorem, even for quadratic number fields, is not entirely obvious. Okay, that one allowed us to give, Mahler's criterion allowed us to prove a general result which specializes to something like, which has as a very special case Dirichlet's unit theorem for quadratic number fields. And in fact, it will also give you Dirichlet's unit theorem for arbitrary number fields. Okay, it can also give you finiteness of class numbers. So it's a very powerful thing. This was actually the hard part, though it may not appear that way. So the next thing is Q is isotropic, and we want to show that G of R mod G of Z is not compact. Okay. So again, actually, since Q is isotropic over Q, it is easy to show that there exists V and W in Qm with the property that Q of V, which is the same as BQ of VV, and Q of W are 0, but BQ of VW and BQ of WV are equal to 1. Okay. In other words, I'm saying that if a quadratic form is isotropic, then you can choose a matrix for that quadratic form which contains 0, 1, 1, 0 as a block. Okay. How do you prove this? Look at the proof that if you have a symplectic form, you can get a 0, 1, minus 1, 0 as a block. This proof is exactly like that, but you have to use the fact that Q of W or Q of WW is 0 for some non-zero W. Okay. From that, you can show that SO, the special orthogonal group, contains the special orthogonal group of the subquadratic space formed of V and W, and that you can check is isomorphic to GM. Remember that GM was equal to GL1. So your algebraic group contains a copy of GL1 over Q. Okay. So quadratic form being isotropic over Q was equivalent to the algebraic group containing a copy of GM over Q. Okay, that is the algebraic group being isotropic. Okay, so actually, I'm running out of time. So let me kind of skip this part of the proof. Okay, so you can use the fact that if you have a copy of GM inside GL1 inside G, which acts on a vector space, there exists some vector which is scaled by a which GM scales by some power, and that you can use to construct a sequence Wn so that Q of Wn is going to 0. Okay, so let me actually not give more details. So let me just skip this part. Okay, anyway, this is the easier part of the theorem, though it may not appear that way. In fact, it should be possible to prove this without using Mahler's theorem. So in some sense, this proof is anyway fraudulent because it uses what it should not need. Okay, so let me make some more remarks. Any questions so far?
So I have a question.
Yeah.
So it seems like this theorem satisfies the local global principle. By that way,
sorry, what does it mean to say that this theorem satisfies local global principle?
Means locals, it is for local field. It is true that it is compact when the Q is. You have already mentioned that easy part. And
no, I have assumed that Q is isotropic over Q. That certainly means that Q is isotropic over R, but a global principle, local global principle would be actually going the other way around. If you knew that Q was isotropic over each QP, can you conclude that Q is isotropic? that is true.
That is the question. I'm doing that by using that local information, can you give this global information?
No, so I have not used local information. This whole thing, so far the way that I have done is actually, yeah, okay. So the thing is, yeah, so what I have written here, I have used global thing, but you are right. Actually, yes, I think you can prove it purely locally in a sense. Namely, you can just look at G of R being isotropic, but then you have to do a little bit of work to show that, G of Z is not too large. Okay. You have to do something like that step I skipped. But this step is kind of local, but it's not like a local global principle, I think.
It's okay, I understand.
Okay, so yeah, anyway, we can discuss that later. Okay, yeah. So let me make some more remarks here. So I have already stated that if a quadratic form is isotropic if and only if the corresponding linear algebraic group, special orthogonal group, contains a copy of GL1, that is, it is isotropic as a linear algebraic group. In fact, the second argument, what I said was easier, generalizes, and you can use it to show that if G is a linear algebraic group contained in GLM and G is isotropic over Q, then that is if G contains a copy of GL1, then G of R mod G of Z is not compact. Okay, where G of Z is defined as G of R intersection. So G of R is contained in GLM of R. So you just intersect with GLM of Z. Okay. So one very non-trivial result of Borel-Harish-Chandra is that the converse is also true. If G is anisotropic over Q, then G of R modulo G of Z is compact. Okay, that's not obvious at all. Okay, in the previous page, I sketched a proof that this is true if your group G is a special orthogonal group. But Borel and Harish-Chandra are proving that this is true for any at least reductive linear algebraic groups and probably for any linear algebraic groups. Okay, so the slogan to remember is this: G of R being compact is equivalent to G being anisotropic over R. G of R modulo G of Z being compact is isomorphic to, is equivalent to G being anisotropic over Q. Okay, so the first one is a question in some sort of local harmonic analysis. It is much easier. Second one is actually subtle number theory, and it is it's actually a number theoretic statement and much more difficult. Okay, any questions? Okay. So we have already seen what is G of Z very informally. Let us study that systematically. Okay. If we try to make that systematic, we will arrive at the notions of congruence and arithmetic subgroups. So SLMs of Z in SLM of R, we want to generalize this to more general linear algebraic groups. Okay. So I'm going to define congruence and arithmetic subgroups. So let G be a linear algebraic group which is contained in GLM over Q. Okay. A subgroup gamma of G of R is said to be an arithmetic subgroup if, okay, so we don't want to define an arithmetic group to be just G of Z. As I told you, G of Z itself is not a purely well-defined notion. If you replace your representation by an isomorphic representation over Q, you are going to get a different G of Z. Okay, so G of Z itself is not well-defined, but G of Z is actually well-defined up to a finite index subgroup. Okay, so a subgroup of G of R is said to be arithmetic if it is commensurable with G of Z, which is G of Q intersection GLM of Z. That is to say that a finite index subgroup of gamma is also a finite index subgroup of G of Z. Okay, so if you define arithmetic this way, then the notion of arithmetic is independent of the, it depends, first of all, it depends only on the isomorphism class of the representation, but it's in fact independent even of the isomorphism class of representation. Okay, it only depends on G as a linear algebraic group G over Q. You can choose any representation you like and define arithmetic using that representation, and that depends, that's an independent notion. Okay, so that's the notion of an arithmetic subgroup. The second notion is the notion of a congruent subgroup. Okay, congruent subgroup is similar to the congruent subgroups that we see for modular forms. Okay, so it's if it contains for some n, gamma is a congruent subgroup if it contains a finite index subgroup of the following form. Set of all G in G of Z. And remember that G of Z is contained in GLM of Z. All G which has trivial image in GLM of Z mod NZ. Okay. So just think of GL2. Okay. We are looking at all matrices in GL2 of Z which are congruent to the identity modulo n. Okay. So they have to be of the form 1 plus an, bn, cn, and 1 plus dn. Okay. In modular forms, we see that, right? Gamma 1 of n or something like that. So those groups which contain such groups are called congruent subgroups. Okay. So first of all, the one thing that we have, and I'm going to skip, is that this notion, both these notions are independent of the choice of the embedding of G into GLM. It can be proved. And notice that GLM of Z contained in GLM of R is a discrete subgroup. And from that, it follows that G of Z in G of R is discrete. So arithmetic and congruent subgroups are discrete. And therefore, being discrete subgroups, G of R modulo gamma is always a manifold if gamma is an arithmetic or a congruent subgroup. And moreover, at least if G of R is unimodular, then G of R modulo gamma has a G of R invariant measure. Okay, just like we saw with SLMR modulo SLM of Z. Okay, and it's also easy to see. It's very easy, but let me not do it. Any congruent subgroup is arithmetic. Okay, so that's kind of obvious. The converse is not true. Okay, but often for many groups, the congruent any arithmetic subgroup is also a congruent subgroup, and this is what is known as the congruent subgroup problem, on which there is a lot of work by Raghunathan, Gopal Prasad, Margulis, and so on. So okay, I don't remember the names exactly, but but it's a very well studied problem. Okay, but typically for higher rank groups, congruent subgroups are arithmetic subgroups, but arithmetic subgroups are also congruent, but for SL2, it's certainly not true. Okay, and in literature, there seem to be some slight variations. I'm not completely sure. Anyway, I'm not an expert in this area. Okay, so the next comment is that, question.
Just a small question. So can you give examples of congruent subgroups and arithmetic subgroup to keep in mind?
So I have already given an example of a congruent subgroup, right?
Yeah.
And every congruent subgroup is an arithmetic subgroup.
Oh, okay, fine.
Okay, but if you want an arithmetic subgroup that is not congruent, one thing one can do is that show that SL2 of Z has as a quotient a copy of alternating group on maybe more than 9 letters, A9, and you can show that no SL2 of Z mod NZ has such a copy, has such a quotient. Okay. And therefore, such a once you have such a quotient, its kernel is going to be arithmetic, but it's not going to be congruent. Okay. Therefore, arithmetic groups are a bit they can be really weird and it's difficult to study them, whereas congruent subgroups are much nicer and they can be studied using adels. Okay.
Thank you.
Yeah. Any other question? Okay, let me go ahead. Okay, so we can define all these things with Q replaced by any global field K as infinite. So, where we you can adapt the definition to any set S of places of the global field K which contain all the Archimedean places. Okay, maybe it has to be non-empty in the function field case. And instead of N, you have to replace it by an ideal in the ring of S integers. Okay, and let me not recall these definitions. One can make these definitions because I'm running out of time. Okay, so you see, there is a slightly confusing point which I had to actually clarify with a colleague, because if G is only defined over R, how do you define a notion of an arithmetic subgroup of G of R? The notion that I defined was for groups G which were defined over Q. Okay, so the point is, you can define the notion of an arithmetic subgroup of a general G of R by considering various possible rational structures on G, but the precise definition needs a little bit more care. You might be able to, let me not go into it. Okay, we don't have time. Okay, so let me state the problems involved in reduction theory. And also let me discuss some of the consequences of reduction theory. Okay. So if reduction theory, first of all, tells us when is G of R modulo gamma is compact, when gamma is arithmetic or congruent. It answers the question of when G of R mod gamma has finite volume. Okay. So if a discrete subgroup gamma contained in G of R has finite co-volume, that is G of R mod gamma. Remember that I said that G of R mod gamma can be given an invariant measure, which is unique up to a scalar. So whether or not it has finite volume is well-defined, independent of the normalization of the measure. So finite volumeness can also be answered by reduction theory. Third is that, just like for SLM of R modulo SLM of Z, we constructed some fundamental domains using the Iwasawa decomposition. Can you construct such fundamental domains and prove that they are approximately, can you construct such approximate fundamental domains and prove that they are approximate fundamental domains? Okay, so these are answered by reduction theory. And if you have reduction theory, for instance, you will be able to come up with groups that act on the upper half plane properly discontinuously, such that the quotient H mod gamma is compact. For SL2 of Z, we saw that the quotient as H mod gamma is not compact. How do you construct gamma so that the quotient is compact? Okay, so there are many constructions, but this will allow you to give such constructions which are arithmetic in nature. Any arithmetic group you can show is finitely presented, that is defined by finitely collection of generators and relations. Okay, so the definition that I gave in the previous pages did not tell you whether an arithmetic group is always finite, right? You have taken G of R and intersected with GLM of Z, right? GLM of Z is a very weird group. Why is that intersection even infinite? So in general, apart from some pathological cases, like, for compact orthogonal group is a pathological case, compact intersection discrete is finite. Outside such pathological cases, gamma is arithmetic groups are not only infinite, but in fact they are Zariski dense. Okay, so this is called Borel's density theorem. So again, these are highly non-trivial theorems, all of which reduction theory allows you to answer. Okay, and finally, if you have an arithmetic group gamma, usually you should not expect the normalizer of gamma to be very large. Okay, what is the normalizer of SLM of R? SLM of Z inside SLM of R. But you can ask instead what is the approximate normalizer? Set of all G so that G gamma G inverse is not equal to gamma, but is approximately equal to gamma. That is, up to a finite index subgroup, it is equal to gamma. That's called commensurator. It allows you to identify G of Q as the commensurator. Okay. Any question?
Yes, but in the reduction theory, is there any role of quadratic form?
Yes. So I told you that G of R mod G of Z is compact if and only if Q is anisotropic, right?
Yes, that's what I'm
so
looking
reduction
for.
theory is generalizing that. Yeah, so it's not what you say, it's not going to use that to generalize it. It's going to be an independent generalization which will recover the quadratic form case as a special case.
Oh, I see. Okay.
Yeah. Okay. So by the way, the fact that gamma has a large approximate normalizer or commensurator is sort of the reason why modular forms have things like Hecke operators, so many symmetries. Though on G of R mod gamma, you might want the normalizer of gamma to act. But if you have only an approximate normalizer, you can make up by averaging and so on. So functions on G of R mod gamma have lots of symmetries. And from those symmetries, you can extract number theoretic information. Okay. So let me go ahead and see the study of arithmetic groups, subgroups in general is actually going to be very complicated. And therefore, but it so turns out that congruent subgroups are much easier. You see, as answer to Sundar Narasimhan's question, I kind of casually mentioned that congruent subgroups can be studied using adels, right? I hope adels have been discussed by Karthikeya in this series. So I want to explain why adels actually allow you to study congruent subgroups. Okay. So what the congruent subgroups, what adels allow you to study simultaneously is, it allows you to study simultaneously the various G of R mod gamma where gamma varies over congruent subgroups. Okay, it does not allow you to study arithmetic, but congruent subgroups it certainly allows. So as a special case, let me consider the group GA. Okay, what is GA? Okay, don't get scared if you haven't seen this before. GA is simply the affine line over Q. Okay, what is A1? What we usually write as A1, right? A1 of Q is just Q, right? A1 of anything is just itself. Its coordinate ring is just Q of X, polynomial ring in one variable. Okay. Instead of viewing it as just an affine variety, the affine line is being viewed as an algebraic group under addition. Therefore, we are calling it GA. Okay. So let me illustrate this principle with GA. Okay. So how do you study? So what is GA of R? GA of R is just R because it's just an affine line over R. Okay. So what are the congruent subgroups? You can embed GA into GL2 by sending X to 1, the matrix 1, X0, 1. Okay. So if you use that, you can verify that congruent subgroups inside GA of R, which is R. So as a subgroup of R, the congruent subgroups are simply the fractional ideals P over QZ. Okay. So if you want to study the congruent subgroup of R together, you want to form an inverse limit out of them. Okay. Inverse limit over P of Q R modulo P over QZ. Okay. Which is the same as inverse limit over integers n R modulo NZ. And if you want to study those, you see all of these P of QZs are contained in the rational numbers. So let us first restrict R to Q and study the inverse limit over P over Q of Q modulo P over QZ, or the inverse limit over N of Q modulo NZ. Okay. So to study this inverse limit, we are going to consider inside inverse limit of Q mod NZ, we have something which we already know. Inverse limit of Z mod NZ. Okay. This is known as the completion of Z with respect to its, this topology, you can call it the congruence topology. And that inverse limit is called Z hat. And by Sun's theorem, which is known less politically correctly as the Chinese remainder theorem, Z hat is a product of copies of ZP as P varies over prime numbers. Okay. Now, if you look at the inverse limit of Q mod NZ, it is a Q vector space. Okay. So the individual Q mod NZs are not a Q vector space, but that inverse limit is a Q vector space. So inside the inverse limit, we got a copy of Z hat, but we can get a copy of something slightly bigger. Okay. We can localize Z hat at the non-zero integers, namely Q tensor over Z hat maps into inverse limit of Q mod NZ. Okay. So it's a group homomorphism, and you can check that this is an isomorphism of topological groups. Okay. Now, if you look at Q tensor Z hat, it is like you are looking at Z hat, which is the product of ZP. But inside that, because you are tensoring with Q, you are allowing finitely many denominators. Okay. So in other words, you are actually taking the restricted direct product of all the QPs. Okay. Because you have only finitely many denominators, most of the places you are actually putting ZP instead of QP, and that's the same as the ring of finite adels. Okay, notice that each Q mod NZ is not a ring, it's just a group. NZ is not an ideal, but this inverse limit is actually a ring. This is the ring of finite adels. Any question? Okay, so, by the way, in all these things, I might be making some small mistakes because, I haven't seen this written down. Okay, maybe not in this particular form. So, and I didn't read the detailed treatment, so I might be making some small mistakes here or there. So remember, our aim was to compute the inverse limit of R mod NZ. Okay. So we have computed the inverse limit of Q mod NZ and identified that with finite adels. Okay. So to relate that to inverse limit of R mod NZ, you write R as the direct sum of Q and a vector space complement, Q vector space complement, right? R has a Hamel basis as a Q vector space. Okay. And at some point, we will not want to deal with a Q vector space complement. And therefore, instead of the Q vector space complement, we might as well put the whole of R by adding a copy of Q to it. But then we have to compensate that by quotienting out by a copy of Q. Okay. So delta of Q means Q sitting inside R cross Q diagonally, A mapping to A comma A. Okay. So then we will use the computation in the previous page to compute the inverse limit of R mod NZ as abstract groups. So this inverse limit, see, the inverse limit only affects the Q part. It is not going to affect the Q vector space complement part. Okay. So its Q vector space complement directs from the inverse limit of Q mod NZ. And then by the same diagonalization trick, you can think of it as R cross the inverse limit of Q mod NZ modulo the diagonally embedded Q. Okay. But we have already seen what is the inverse limit of Q mod NZ. That was R cross the ring of finite adels. So we get that inverse limit of R mod NZ is R cross finite adels modulo the diagonally embedded Q. But R cross finite adels, if you remember the talk on adels by Karthikeya, it's just the ring of adels. Okay. So the inverse limit of R mod NZ is just the ring of adels. Okay. In other words, it's a restricted direct product of the various completions of QV, completions QV of Q, except that at almost all places, you must have an element in ZP contained in QP. Okay. So this is adels are again a ring. They contain Q. They have a topology. So they are a topological Q algebra. Okay. And henceforth, instead of A mod delta of Q, we are just going to write A mod Q. So in other words, in the restricted direct product, which is the adels, Q sits diagonally. Okay. So check that this inverse limit computation, inverse limit of R mod NZ as A mod Q holds topologically as well. Okay. So A mod Q is some sort of a solenoid. It is an inverse limit of circles mapping to each other by their n power maps. Okay. So let me make a few more comments regarding adels. So in other words, we saw that the ring of finite adels was the inverse limit of Q with respect to its congruence topology. Okay. In other words, Q modulo its congruent subgroups. Okay. So though AF itself was an inverse limit, A is not an inverse limit. It is A mod Q which is the inverse limit. A mod Q is the inverse limit of R modulo it's the congruent subgroups. Okay. So if you look at the definition of the topology on a completion or an inverse limit, it follows that the congruent subgroups, the fractional ideals of Q, are precisely those obtained by as the various Q intersection KF, where KF runs over open subgroups of AF of finite adels. Okay. So that's just the topology on completion. How does it relate to the topology on the original group? Okay, it's just that sort of thing. I mean, one can also check this directly. So, well, I haven't seen a general theorem which specializes to this, but at least one can check this directly. Okay, so a congruence condition is simply a compact open subgroup of finite adels. Okay, so that's a slogan. Maybe I should have written this as a slogan. A congruence condition just means a compact open subgroup of the finite adels, just like the kernel of the map from Z hat to Z hat mod NZ hat. Except that we are also allowing some denominators. Okay. So if gamma is P mod QZ, which is Q intersection the compact open subgroup KF, then you can see what is R mod gamma going to be. After all, what was our goal? So I'm going to take maybe a bit like 5 or even slightly more minutes because I want to really complete this. Otherwise, the next talk is going to be it'll be difficult to have a nice starting point for the next talk. Is that okay, Sazzad?
Yes, it is okay. Please go ahead.
Thank you. Yeah. So I'll not proceed after this topic is over, but I need to complete this topic involving adelic points. Okay. So R mod gamma, we use the same trick. We put an extra copy of Q and quotient out by the diagonal Q. And then this time you can bring the gamma onto the right hand side. Okay, so you can write it as R cross Q mod gamma modulo diagonal Q. Okay, so that diagonal Q allows you to absorb all the Q from the Q mod gamma, but then there is some gamma which remains, which latches onto the R. Okay, so this is a very elementary group theory isomorphism, but Q mod gamma is just AF mod QF, KF. Okay, so in other words, R mod gamma is the quotient. After A mod Q, you further quotient on the right by a KF. Okay, so this is going to be the general picture. The various G of gamma various congruent subgroups gamma are going to be dictated by open subgroups of G of AF, and similarly G of R modulo gamma in general will be related to G of A modulo G of Q right modulo KF, where KF is a compact open subgroup of G of AF. Okay, so now let me discuss topologies on adelic points. So whatever we saw for the group GA right now is a lot of that is going to work for linear algebraic groups over Q. So let me discuss topologies on adelic points. Here I really need 5 to 10 minutes. So please bear with me. So suppose X is a finite type, you see affine variety or a scheme over a, usually affine variety or a scheme is defined over a ring R, but this time we are considering a topological ring R. Okay, so adels have a topology, finite adels also have a topology. Okay, so a variety or a scheme is just a bunch of equations, and X of R is just the solution to that system of equations over R. Okay, so X of R is usually only a set, but if R is a topological ring, you can also think of X of R as a topological space. You give it the weakest topology with the property that, if you have an affine variety X, you have the notion of a regular functions f on X. For every regular function f on X, f gives you a map from X of R to R, right? R already has a topology. So you require that all of these functions X of R to R be continuous, and you give X of R the weakest topology with this property. An equivalent way to topologize this is you embed X in an affine n space as a closed embedding. Okay, closed embedding because you want regular functions to surject. Okay, so then X of R is actually going to be contained in Rn. Since R has a topology, Rn can be given a product topology, and therefore X of R can be given the induced topology. Okay, so for Lie groups, this agrees with the usual Lie group topology on GLM of R and so on. Okay, so this is how you can topologize X on X of R for any topological ring R. So for instance, if you take X to be GL1, GL1 of R is just, GL1 of adels is just the edels, and what you recover this way is precisely the usual topology on edels. Okay, that is why you have to choose a closed embedding and not embed GL1 into the affine space, but GL1 into the affine 2 space. Therefore, if G is a linear algebraic over Q, okay, you can make sense of G of R for any ring R containing Q. In particular, A and AF, they are both rings containing Q. So therefore, G of A and G of F are well defined as sets. You see, G is a bunch of equations. G of A and G of AF are the solutions to those equations over A or AF. But A and AF have a topology. So by whatever I just described above, G of A and G of AF are not just sets, they are actually topological spaces. And since they are also groups, G was a linear algebraic groups, these are actually topological groups. And since they can be embedded in some affine n space, these are actually locally compact topological groups. Okay, so if you did not want to listen for the last 2 minutes, the moral is that if G is a linear algebraic group over Q, then the adelic points of G as well as the finite adelic points of G make sense, and they are locally compact topological groups. Okay. So one way to think of the topology is that you embed G inside SLM over Q. So G of A is contained in SLM of A, and SLM of A is contained in A to the m squared, and you can give the product topology on A to the m squared and restrict to G of A. Okay. Because these are topological groups and second countable and all that, they have Haar measures. And because Q inside A is discrete, it follows that G of Q inside G of A is discrete, and therefore G of A mod G of Q has a quotient measure. Okay. An alternative measure is that if you choose equations for G over Q, these are defined over ZP for almost all P. Okay, let's say outside P element of S, and therefore you can make sense of G of ZP, and you can also realize G of A, the A points of G, as a restricted direct product of G of QP with respect to the G of ZP. Okay, so this was how I think Andre Way, etc., conceived of the topology on G of A. But Brian Conrad's paper is a very nice expository article. He makes these notions of point topology on adelic points very easy for ordinary people to understand by describing it in the manner that I have described at the top of this page. So I highly recommend reading this paper of Brian Conrad called Weil and Grothendieck Approaches to Adelic Points. Yeah. So Conrad has made many things easier for us to kind of deal with by writing lots of nice articles like this. And although I discussed only Q, everything I have said so far generalized to other global fields. Okay, so let me discuss this slide also because this belongs to the same topic. Okay, so how can we study congruent subgroups of G of R? Okay, so these are precisely G of Q intersection KF as KF runs over compact open subgroups of G of AF. Again, this is the same philosophy that finite adels capture congruent subgroups at the level of Q points. Okay, so this is the thing to remember. Earlier, the definition of congruent subgroup used an embedding of G into some GLM, and then we had to prove that definition of a congruent subgroup was independent of that embedding. But here, you can define congruent subgroup just using adels without using any sort of choice of a representation of G into a GLM. Okay. Just like finite adels were the inverse limit of Q mod its congruent subgroups, and just like A mod Q, at least G of AF is the completion of G of Q with respect to its congruent subgroups. I'm not so sure about G of R mod gamma, but at least mentally, to kind of relate to various G of R mod gamma, I think of G of A as mod G of Q as some sort of a inverse limit of G of R mod gamma. Although neither of these statements is true for arbitrary linear algebraic groups, it's only true for groups that satisfy strong approximation. Okay, which is roughly like, saying that, G can be sort of studied using copies of GA in it. That's not exactly true. But these things work like it worked for the group GA. Okay, so the questions, we were interested in questions like whether G of R mod gamma is compact or finite. So since G of A can be related to the various G of R mod gamma, those questions can be reduced to analogous questions about G of A modulo G of Q. Okay, so if so you see, if KF contained in G of AF is a compact open subgroup such that KF intersection G of Q is gamma, I said you can always choose such KFs, then the quotient of G of A on the left by G of Q and on the right by KF is not quite G of R mod some gamma, but it's a disjoint union of some G of R's mod gamma. Okay, so if you study one G of A mod G of Q, you can study any G of R modulo gamma, and compactness and finiteness of volume, it's enough to study G of A mod G of Q, and all of these generalize to more general global fields. Again, arithmetic subgroups are really weird. You cannot study them using just adelic points, but the magic of adelic points allows you to study all congruent subgroups at one. And basically, all that this made this work was basically our good old, Chinese person from maybe a few centuries BC or AD, I don't know, Sazzad, namely Chinese remainder theorem, allowed you to view Z hat as a product of Z mod NZ. So, study of congruent subgroup could be studied in terms of products with a few finitely many denominators thrown in, which basically was some sort of adelic points of linear algebraic groups. Okay, so that's roughly what we discussed just now. Next time onwards, I'll start getting into the question of when G of A mod G of Q is compact. But I have stopped. I haven't discussed anywhere near how much I plan to discuss today. But anyway, what to do? So I'll continue from here. I'll share the slides with Devendra. I hope they will be put up. Devendra, will you put them up?
Yes, we will be putting on the web page.
Thank you. So you can look at both these slides and last time slides, so that you can come to the next lecture. When you come to the next lecture, you can at least familiarize. I mean, you don't need to worry about the proofs, but at least you can familiarize with the objects if you are not very familiar with these. Okay. And please keep in mind, I might have made lots of mistakes here and there. I'm just trying to convey the main idea of things, etc. Okay. So, any questions?
Let's thanks first. Let's thank
Thank you.
Professor Sandeep for the nice talk. So, are there any questions? So, I have one question because your first talk I did not attend. So, could you go to your first slide for today?
Oh, today's first slide. Okay, that I can go. Yeah.
Yeah. No, the question you put the second slide then.
No. Okay.
Yeah. Question. Yeah. No, not this one. Page 2 then.
Here?
Where did you put question?
Where?
Is it compact or not? That question you put. No. Before that.
Yeah. Why
What
is
was
this?
my question? Motivation of studying this quotient of GR mod GZ. It is compact or not? That motivation I want to know.
Why are we studying whether G of R mod G of Z is compact? Is it?
Yeah, that is the question.
So already I explained in the case of even for very simple quadratic form x square minus dy square, right? That compactness contained Dirichlet's unit theorem in a special case, right? So the work of Borel-Harish-Chandra is a vast generalization of both Dirichlet's unit theorem and finiteness of class number. Okay.
Okay.
And not just that, you see, I also in a later slide, I also talked about some consequences of the above answers, right? You can
Yeah, but
show that
here I tried to understand that maybe it is connected with this slide. So that doesn't I ask that question also. How to bring Q a quadratic form here to the reduction theory.
Sorry, how to?
So in this page is about the reduction theory, but
So the
question,
thing is, So the thing is, reduction theory is asking when is G of R mod gamma compact when gamma G is a linear algebraic group over Q, right?
yeah.
If you take G to be associated to a quadratic form over Q, the special case is the reduction theory for the quadratic form that I discussed at the beginning of the talk.
Okay.
Yeah.
I understood. Okay.
Yeah. Sorry, maybe I should have kind of more explicitly said that, clarified that.
Okay. So, are there any more questions? If there is no more question, let's thank Professor Varma for the nice talk.
Thank you. And I hope to see you next time.
Yeah. Hopefully, see you soon.
Yeah. Thank you very much.
Thanks, Sazzad, for coming for the chair also at the short notice.
Yeah, thank you, Sazzad.
Okay,
and nice
thank
to
you.
meet you. Yeah.
Nice to meet
Okay, so we'll meet again on Tuesday for the next talk of
Yes. Thank you, Devendra.
same time.
Yeah.
Yeah, so we will be closing the meeting now.
Yes. Thank you. Yeah, sure.
Okay, Sandeep.
Okay, Sazzad. See you. Yeah. See you.